24. We're almost to the end. Hello. 24. Okay. Actually, okay. So real quick, I just want you to look at the 2 pages, and you can look at them side by side or flip. But notice how these pictures are not on grid anymore, right? So we can't talk about how many units we've moved, right? And then unless it's marked with a right angle or it has like a straight line joining it, we really can't even talk about like degrees, okay? You technically don't have a protractor to measure it all. So how do we describe these transformations that are not on grid when we can't count units or talk about angles? So it's just another set of phrases for mapping onto. It's not hard, and a lot of times they're used in multiple choice questions, but I want to show you how we can state them. So here we have ABC, and it's mapped onto EGF. So what transformation is it? Translation. Great. So it's a translation. But stopping there is not enough. No. So how can we describe it when we can't say left and down, and we're not using like south by southwest? What can we say? Well, we can use the phrase maps onto. So if I were looking at side AB, what is AB going to slide onto? EG, right? So are those corresponding sides? So we literally are just going to talk about corresponding sides and talk about all of them so everything maps on to the right spot and rigid motion is maintained. Yes?
Why can't you say you're on the right and down?
Because how far right, how far down? It is a sticky wicket. So what would you put? So this is what you would put. So translation, so that AB maps onto EG. Okay. Let's do now BC. What is BC going to map onto? Yeah. Yep, onto GF. And what other side do we need to talk about? Yep, AC. Yep, maps onto EF. Good. Okay. So that is a lot of words, but actually what we just did was something called side, side, side. Did we just move all 3 sides onto the other 3 sides?
Yes, we did.
So since they're mapping on perfectly, we know these triangles are congruent by side, side, side. Now there was, if you go back, and now this is hard, go back to page 18 for a second. Find it, page 18. Find page 18, you can do it. You really like me. Find page 18. All right. Do you guys remember me kind of talking about this BQ equals radical 29? And I said, well, where in the world is BQ? Well, BQ is this purple line, right? That connects one triangle to the other triangle. And we found out its length was radical 29. That's called a vector. So another way to explain it, and it's not used very often, but it is another way to do it, going back to page 24, is we can pick any 2 corresponding points and connect them, with a straight line, which that didn't work out. Erase, drawing. So I'm going to use my, there we go. So connect B to G, and I'm going to put an arrowhead on it, like a ray. And that can be called a vector. So we would say all points of triangle ABC are translated using vector BG. And what's special about a vector is it has distance, like a segment, but it also has direction. Come here, get out of here. Go, 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 go. Direction. And let me just do this real quick. So this is kind of cool. Like I can pick up this vector and I can move it and I can go to any set of 2 points that correspond. And you see how it's always the same distance?
Yeah.
And it's because of the, so like this point is translated to that point. So that's why we say all the points are being moved. It's an infinite number of points between the 2 endpoints. Cool? Okay. So it's rare that a vector comes up, but that square root of 29 kind of threw me off when they put that on last year.
What is a vector again?
It is, like this line is called a vector.
Okay, so it's like a line that defines that all.
Defines distance and direction.
Okay, sounds great.
So if I were to draw just this line, well, A moves to B that way, but that doesn't work for C moving. Like, you know what I mean? Like,
Yeah.
they don't, this vector doesn't work. It's too short, it's pointing in the wrong direction. So hopefully you won't have to know vectors, and then we can talk about how I could actually find the length of this using Pythagorean theorem if I had the other lengths. But I don't have any lengths, so that's why mapping onto is easier. Okay, let's get to the next one. That was the weirdest one. These other ones are easier. Okay, how do we reflect, dang it, I said it. How do we map ABC onto DBC? So find the 2 triangles. Where is ABC? ABC. How do we get that triangle onto DBC?
A reflection over the line BC.
That's it. That's all you have to say. It can be that easy. Okay, the mapping onto one was weird, but those guys were weird. Okay, let's try another one. So now, number 3. How do I map ABC onto DEF? So, is it a translation? Are corresponding sides parallel?
Yes.
Okay, focus.
Oh no.
Is AB parallel to DE? Right? Those are corresponding sides? Not parallel. Okay, so then what transformation is it? Is it reflection or rotation?
It's rotation.
Okay, very good. So when we talk about rotation, we have to talk about a center and a degree, but we can't use degrees, but we can talk about a center. Did they give us point K?
Yeah.
Yeah, and if I connect K to C, Kentucky Fried Chicken. Oh, it is Kentucky Fried Chicken. Look at that.
Oh yeah.
KFC, baby. Ow! Okay. Can we tell that we're going counterclockwise?
Yes.
Okay. And we can tell that K is the center. So what could I say about mapping? What needs to map onto what? Where does point C need to go?
90 degrees.
Is this a right angle, buddy?
Oh no.
No, you can't, it's not marked, you can't use degrees. But can we say it maps onto point F?
Yeah.
Yes. So rotation, counterclockwise, centered at K, so that point C Maps onto. Oh, that's 2, not onto. Maps onto F. The likelihood that you're going to have to explain these is minimal, but being able to see rotation, see reflection, these are the things we're working out today. Yeah? Yeah. Okay. Ready to go to the next page. Beep. We're doing great. All right. So take a moment on this one. Do the triangles look like they are congruent? No. So if triangles are not congruent, then dilation was used. But I usually don't worry about dilation until part 2. Let's just kind of look at some stuff. So notice how the triangles both have the letter C in them. And then it says A, B, C, D. Yes! Awesome sauce.
Awesome sauce. Just like you, Miss
C
Rob.
is the center. The center of what? Both things, right? Center of dilation and center of rotation. Because guess what? A has to map onto D. How many degrees?
It looks like 180, but
It's a straight line. No, is it a straight line? A straight line?
Yeah.
Yes. So it is 180 degree rotation. Okay. Good job. So I'm going to put it. C is the center. We'll do it a little sloppy. Center. Okay. So step 1 was rotation, right? And we put the details over there. Rotation with details that way. Details.
Could you also say point reflection?
You could do point reflection, yes. Point reflection through point C.
Okay.
Nice job. Okay, but we now have to deal with dilation, right? Is our triangle getting bigger or smaller? Smaller, but we don't have a number for scale factor because there's no numbers anywhere. But we do have scale factor is an image divided by something from the pre-image. So we dilate. Think about that the center is still point C, right? And then our scale factor, so we need a side from the image.
I think we should do BC and CE.
Okay, so if we do BC and EC, which one is the image side?
I think
We're doing this onto this.
Oh, the image would be CE.
Okay, so if we say CE, then what's going to go underneath it? BC or CB. I usually try to keep my letters in order. Does that make sense? So this length over that length, or like let's just pretend if it was 6, 6 and 7. Okay, so anyways, there you go. Ha ha ha! Miss Rupp is into it.
I know.
6, 7.
Oh yeah, Miss Rob.
Ready? It's everywhere. I don't know what happened and like where people's brains have gone. They're fried.
Oh, silver.
It's everywhere. Yeah, steel brain rot is killing people. Anyways, yeah, you're
Probably dead now.
fajuli, whatever. Okay, so have we seen some examples of how this works? Let's look at 2 regions questions. Go. So focus.
I'm so sorry.
In regular hexagon. Ooh, what does the word regular mean?
Regular. That means regular.
No.
Normal.
What? Normal.
Conditions.
It doesn't have gas in its belly? I mean, it's regular. What's going on here?
It's that regular shape.
Regular. What's true about all the sides?
No gas in his belly.
The sides are all congruent. What's true about all the angles?
They're all congruent.
That's right. Is a rectangle a regular quadrilateral?
No.
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 Okay, regular means all sides. That thing that you rotated, the little house guy, was not a regular pentagon, right? That was not. Okay. So in regular hexagon, A, B, C, D, E, F, shown below, we have all these different diagonals intersect at G. Okay, here you go. You need to interact with the picture. When triangle A, B, G, find it. You can draw it on your picture. Where is A, B, G?
This way, Dean.
Is reflected over BG. So where is it now? Figure out where it is.
Hold on.
What? That don't even make sense.
Okay, so here we go. When triangle ABG is reflected over BG. So is B going to go anywhere?
No.
Is G going to go anywhere?
No.
Where's A going to go?
C.
To C. Okay.
Does how you have different color highlighter to like do that?
I'd be happy to.
Yes.
I have lots of versions of yellow remaining. That's what I got. And then rotated 180 degrees about point G. Where does it land?
F, E, G.
So if 180 degrees, where's it going to go?
Right there.
Right here.
Oh, yeah. I did it. Did you do it, Sophia? Yeah, great work.
So what's the correct answer?
Did you do it, Tina?
And that's choice what? 1?
Yeah.
Choice 1. So guess what? Guys, that was worth 2 points.
Oh my gosh, I got 2.
Do you see how easy some of these questions are?
Yeah.
Do you have to slow down and just do the work though?
No.
Do you have to read real careful?
Yeah.
Not go crazy bonkers. Okay, next question. Are you ready? In the diagram below, ADE is the image of ABC after a reflection over AC, followed by a dilation of scale factor AE over AC centered at point A. Just pause right now. Where was the start? Where was the finish? Who was first?
ABC.
Label your picture. Either pre-image, image, start, finish. Where's the beginning?
ABC.
AD is the start.
ADE is the image
Of ABC.
of ABC. So ABC was the beginning. This is the end. So now, which statement must be true? What are the 4 answers about? What are they talking about? What's that weird symbol?
Angles.
Angles. Okay. So these are about corresponding angles. What's true about corresponding angles? Did they stay the same or did they change? Same. If it's a right triangle when you start, it's a right triangle when you end. Corresponding angles are congruent. Corresponding sides are proportional but we don't have a scale factor that's a number, do we? There's no number that says the scale factor is 1/2. And they're not talking about sides anyways. So can we automatically cross out 2 choices? Which 2 should we be crossing out? 3 and 4. Both of these are poo-poo because there will not be a change. No change. No change. No change. That's bad. Bad dog. All right. Now you have a couple options. You could certainly just trace out the angles to see which one's right. You could say, hey, the first triangle was called ABC. The second triangle is called ADE. So A better be A, B becomes D, and C becomes E. Which one's the correct answer? Choice 1 or choice 2?
2.
2. A, B, C, so this angle right here, is equal to ADE. Right there. Was that a hard question?
No.
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 So, these questions are not hard, but you have to slow down. So, these actually are all Regents questions. Some of them, the ones where actually you have to do the explanation, they are a little bit oddball. And then I put in some symmetry questions at the end because we struggled with that idea. Some people had trouble with that on the quiz.